Hi, good day to you, and welcome to my channel where I tutor you in science for free. The topic in this video will be electromagnetism, and in this chapter you'll be exploring the phenomenon of using electricity to create a effect, say light or movement. And in the next chapter, electromagnetic induction, we're talking about creating electricity from movement. Okay, so let the future worry for itself. In the next video, let's come back to electromagnetism, where we'll be talking about creating a movement from electricity. So in the previous chapter, we covered the right hand grip rule, whereby it talks about the magnetic field lines through current carrying wires, and it follows this direction. The current is coming out of the paper. You use your right hand grip. It is supposed to be in the anti-clockwise direction. It has this notation with a circle and a dot in the middle. And if it is going into the paper, it is a circle with an X. And how do you differentiate between these two? You have to imagine an arrowhead, like a bow and arrow. Coming out of the paper is like the tip of the bow, and going into the paper is like the fletches, the feathers of the arrow. And it also works with solenoids. If the wire is carrying a current and it goes in this direction, then the north will be in this way. And if you look at it carefully, because individual coils, they are all in the same direction and they all add up, creating a total summarized effect. That's what we see using these magnetic field lines. And next we will be covering forces that is generated when electricity interacts with a magnetic field. And this will be introduced to this very cool concept of the left hand rule, the Fleming's left hand rule. Your hand works like a formula itself, the thumb being the force, index finger being the field, and the middle finger being the current in this formation, 90 degrees to each other. A magnetic field points from the north to the south, and there you can see there are three fingers pointing outwards. Usually a situation will give you two information, you have to find the last one. And a very common application of this Fleming left hand rule will be the electric motor, and this will be a very simple schematic of a motor whereby current comes out of the cell, okay, goes through to the carbon brush. The carbon brush conducts electricity as well, and it's not connected tightly, it's not connected dead to the split ring commutator. So the split ring rotates around the two carbon brushes, maintaining contact so that electricity can still flow, okay, and it moves upwards to the AB direction of the coil. So now the effect of the force experienced by AB will be that of using your left hand rule, because electricity directly comes from the cell to create an effect. So it's part of a DC motor, you use your left hand rule. Okay, force, you do not know where's the force. Field, magnetic field, point north to south. Current, okay, points upwards, so you rotate your whole hand to point outwards. Where does your thumb point? It points downwards. As the current travels from B to C, C to D, current, okay, middle finger points backwards, now the thumb points upwards. You can see that there is a circular rotation, and it comes back to the split ring commutator, carbon brush, go back to the rheostat, and back to the cell. And the split ring commutator is split ring because every time it travels half a turn, it will temporarily disconnect from the carbon brush, but the momentum will carry it forward so that the motor does not run dead. And once momentum carries it forward to the other side, the downward force will be applied on the new side of the coil, and vice versa on the other side of the coil. The upward force will be experienced, thereby creating a cycle going round and round. And of course, common ways to edit the motor will be this. To increase the turning effect will be increasing the number of turns in the coil, increasing current, all quite common sense. Okay, your foundation should be built from the previous videos. Increasing current, adding a soft iron cylinder as well. Iron cylinder helps to concentrate the magnetic fields. And that's pretty much about it for left hand rule. And in this chapter, for the next part of this topic, we will cover force on beam charged particles. What this means is when magnetic field is perpendicular into the paper and a moving charged particle is traveling through it, it will experience a force. So similarly, using left-hand rule, force field current, okay, if a proton and positively charged particle is being shot into the magnetic field, use your index finger, magnetic field, point into the paper, and because it's positive, you follow the direction of its movement, the resultant thumb points upwards. So the proton will experience an upward force. If an electron is being shot into this field, because electron is negatively charged, your current finger, the middle finger, has to point reverse direction of the electron's movement. So you point backwards, then the resultant thumb point will be downwards. Let's move on to some questions. Okay, each diagram, when two current carrying wires have their current direction into the plane of the paper, the forces on the two conductors will be inwards, because if you use your right hand grip, you point downwards into the paper, both have a circular clockwise magnetic field lines. The magnetic field lines will merge and they will bring these two wires closer together. So this is a commonly asked concept. Circuit shown, control current is used to switch off high current. When the control current is switched on, the high current does not switch off, which change might switch off the high current. So this is talking about making a electromagnet stronger. Okay, this is done by using a larger control current. Okay, which arrow gives a possible direction for the magnetic force on the cable? There's a direct current in the cable. You don't know, is it pointing into the paper or out of the paper? You have to take that in mind. So force field current field points downwards, diagonal downwards, and the current maybe, let's say, point into the paper. Okay, now I am facing the A option. Okay, A will be the answer. If the current points upwards, it's supposed to be a 45-degree angle also, but it's none of the choices here. So A will be the answer. Which diagram shows the directions of forces on the two conductors? So one points in, one points out. Conversely, it will be away from each other, because if you use your right hand grip rule, one goes in, one goes out. Magnetic field line, one has a anti-clockwise direction, one clockwise direction. They will push each other away in the middle. So you see, it's a commonly asked concept. Similar direction is an attraction force. Opposite direction is a repulsion force. Okay, this is a DC motor schematic. At the position shown, the forces on sides P and Q are vertical and produce a moment about the axle. Why does this moment decrease as the coil turns? Okay, it's because the perpendicular distance between the forces on P and Q decreases. As the axle is turning, the side of the side P of the coil and side Q of the coil moves towards the axle. Okay, and by law of moment, force times distance, it gets lesser and lesser, the moment gets lesser. Okay, let's go on to some written question. Explain why the coil turns when the switch is closed. When switch is closed, okay, use phrases like this to start off your written questions. Current flows in circuit and coil. Since there's a current between magnets, force is produced. One side has a force produced that is downwards, the other side it will be upwards. Therefore, the coil turns by Fleming's left-hand rule. Explain why coil turns, continues to turn in the same direction when it has turned 180 degrees. A 90-degree rotation split ring commutator helps to change the direction of the coil. Okay, this causes the force acting on the coil to go in the reverse direction, so helping the coil to turn in the correct direction and continuously. And that is all for today. Hope you enjoyed this video. Do give it a like and subscribe, and share it with somebody who needs to see this. And I will catch you in the next video. Bye!